All right, so just for the sake of the recording, we're going to talk about algebra's common graphs. I'm just going to repeat the first part. Linear functions are in the form y equal to x, and when you graph a linear function, it produces a straight line. The next type of function is a quadratic function, and it's in the form y equal to x squared, square being the largest power on the variables. It produces a U-shaped graph or parabola. Next, we have a cubic equation, y equal to x cubed. When it's graphed, it produces an S-shaped graph. Next, we have a square root function. It's in the form y equal to the square root of x, and its graph looks as such. The absolute value when it's graphed, or its model form, would be y equal to the absolute value of x. And it produces what's called a V-shaped graph. Right. Now, we'll also talk about how to read these graphs just a little bit. You read graphs just as you read sentences from left to right. So we're going to take this linear equation example. Now, even though we have arrowheads, and these arrowheads allude to the fact that this line just keeps on going forever in both directions, when I read it, I want to read it from left to right. If you read it from left to right and the graph goes up, it's increasing. If you read it from left to right and the graph goes down, it's decreasing. So if I look at this first graph, and if I were asked to read this graph would be an increasing function, because as I read it from left to right, it always goes up. If I look at my quadratic equation, okay, I'm going to read it from left to right. When I initially start to read this from left to right, it actually decreases or goes down. And then it gets to a certain point, and we're going to talk about this point later. That point is called a vertex. Once it hits the vertex, this graph then begins to increase. All right, so it decreases first until we get to a point called a vertex. And then once it hits the vertex, it increases. For my cubic function, okay, or at least the one we have sketched here, as we read it from left to right, it increases. Right? From left to right, it always goes up. If we take a look at the square root function, notice that the square root function, it increases as well. It never decreases, okay, because this thing will like slowly rise forever and ever. And if I look at my V-shaped or absolute value graph, initially when we read it, it decreases, right? And then we get to a point, and on that point, this is called a vertex. The only graph that has a vertex is a quadratic function. Okay? But we get to a certain point on the absolute value graph, and then that graph increases. All right, so that's just a brief stint on increase and decrease and how to read graphs. I'll pull up the shared screen. Okay, and I'm going to go to the lecture notes. Okay, I'm going to pull up section 2.1. All right, so in section 2.1, we're going to talk about graphs of the basic functions. And first, we're going to talk about something called continuity. And a function is continuous, or it has continuity over the interval where you can trace your graph without removing your pencil from the paper. Okay, all of the graphs that we've looked at, these first 5 graphs so far, all of those graphs are continuous, because you can put your pencil on the graph and you can trace the entire graph without removing the pencil from the paper. All right, so the linear, quadratic, cubic, square root, absolute value, those equations are all continuous. Now let's talk about a discontinuous graph, or a graph that has what's called discontinuity. If a function is not continuous at a point, then it may have a point of discontinuity. What a point of discontinuity means, if you're tracing your graph, so I'm going to take this first graph for example, and if I were to read it from left to right, so notice as we read this first graph from left to right, it decreases. And then we get to a point, and in order to trace the graph, we have to take our pencil off the paper, we have to put it back on the paper, and then we can continue to trace the graph. For this first graph, when x is equal to 2, that's a point of discontinuity, because at x equal to 2, we take our graph off the paper, put it back on to continue tracing the graph. The second example is also an example of discontinuity. So here again, if I were to read this graph from left to right, so as I first read it from left to right, the graph increases. But then I get to a certain point where I have to take the graph off the paper, and that point is when x is equal to 2. I have to put it back on the paper and continue to trace the graph. All right, so for the second graph, as x equals to 2, we also have a point of discontinuity. And as we can tell just by reading the graph, the second and the first graph, they're both increasing. So as I read this first part of my graph, it increases. It is discontinuous because I take my pencil off the paper. And then when I continue to trace the graph again, it's still increasing. So just to touch on that increase and decrease concept again. Okay, now on this side, we're just looking at some examples of continuity. So for my first graph, and this would be the graph of a quadratic, a U-shaped graph, I can put my pencil on the paper and trace the entire graph without removing the pencil from the paper. So this graph is continuous on all real numbers, from negative infinity to positive infinity. The discontinuity or the continuity depends upon your x-axis. So this graph is the entire x-axis, and we can draw it without removing the pencil from the paper. If we look at example B, as I trace my graph, notice that when x is equal to 3, there's a hole in the graph. At this hole, if we were tracing the graph, we would have to take our pencil off the paper, put it back on the paper, and continue tracing the graph. The point in which we take our pencil off the paper, that's the point of discontinuity. So the point of discontinuity is x equal to 3. However, if you were to write out the interval of continuity from negative infinity to positive 3, I can trace the graph without removing the pencil from the paper. Right, so my continuous interval is from negative infinity to positive 3. Union, or when I put my pencil back on the paper at or near 3 to infinity, I can trace the graph. Notice that 3 is taken out of the interval because that's the point of discontinuity. And as we can see from this last example, we're going to talk about vertical asymptotes in a later chapter. As a vertical asymptote at x equal to -2, but a slight introduction to a vertical asymptote, it would simply be a vertical line, and it's an imaginary vertical line. So this dashed vertical line is our vertical asymptote. The graph gets closer and closer to this line, but will never ever touch the line. All right, so that's a definition of an asymptote. So if we were to trace this graph from -infinity to -2, right, we can trace the entire interval. However, and that interval is increasing. When we take the pencil off the paper, put it back on at -2 to continue tracing the graph, that graph decreases. But it's continuous on the interval from -infinity to -2, or from -2 to +infinity. And we sort of talked about increasing and decreasing functions. It's just that when you read your graph from left to right and the graph rises, it increases. If you read your graph from left to right and the graph falls, it decreases. Okay, I'm going to skip down a couple of slides. Well, actually to the last slide, where it talks about odd and even functions. And I also want to pull up the calculator to graph, I also want to pull up the calculator to graph some of those common functions so you know how to graph them in your calculator. But here we have the concept of even and odd functions. A function is an even function if f of -x is equal to f of x. And we're going to talk about that formulation in just one second. And an even function is symmetric with respect to the y-axis. A function is symmetric with respect to the y-axis if you fold the y-axis, if you fold the graph about the y-axis and the graph overlaps itself, then you have what's called an even function. An odd function, it's both symmetric with respect to the origin, which is symmetric with respect to the x and y axis. A function is an odd function if f of -x is equal to -f of x. Now, when you're doing the homework on some of these problems, it'll ask you if the function is odd or even. If the function is odd or even, it'll ask why. Here's the y portion. This is what makes a function even if f of -x equal to f of x, and here's what makes a function odd. F of -x is equal to -f of x. Okay, and I'll explain both of these concepts. I'm going to pull up my calculator. Okay. All right. And we're going to take a look at just graphing a linear function. Okay, we're actually going to graph a linear, quadratic, cubic, square root, absolute value. Okay, and then we're going to talk about even and odd. All right, in order to graph a function using your calculator, I'm going to go into y equals, and notice you see y sub 1, y sub 2, I believe all the way down to y sub 0. You can actually graph 10 functions at once. Okay, but I'm only going to graph one function at a time. So I'm going to put in y equal to x. So in order to call up the x variable, you simply want to hit this key. Now, if you hit this key and you get something other than X, let me know. You have to go into your mode. You have to go down to this fourth line where it says function. PAR is parametric, polar. We have sequential. You want to make sure that you're on function. Right, so I have y equal to x. In order to graph, I'm simply going to hit graph. Now, when I graph function in this course, you're going to see me do a couple things. I want to explain what I'm doing. You're oftentimes going to see me, instead of hit graph, I'm going to hit zoom, and I'm going to hit 6, which is standard. So what zoom standard does, it puts your calculator having the x-axis from -10 to +10 with increments of 1. It will put your y-axis as having a minimum of -10, a maximum of +10 with increments of 1. Okay. Also, when you hit zoom standard, all of our calculators and graphs will look exactly the same. Right, so your graph should look exactly the same as my graph. So notice that this graph is increasing. All right, next we'll graph a quadratic equation. I'm going to go back into y equals. I want to graph y equal to x squared. So I already have x, so I'm just going to hit x again. In order to square it, I'm going to use this square key. And if I graph, and here again, our calculator is already in standard mode. Notice it produces a parabola, a U-shaped graph. Next, we'll graph a cubic equation. So I'm going to go back to y equals. So notice I don't have a quick cube key. In order to enter our exponents, I'm going to use this caret. So this is x raised to the third power. Okay, I'm going to graph, and it produces the S-shaped graph. All right, now we're going to graph the square root equation. Y is equal to the square root of x. So square root is above the x squared key. So I put my absolute value function in a set of parentheses. Now, depending upon what calculator you have, you may or may not have to use parentheses. I know the TI-84s, when you put in the square root, it'll just sort of capture everything under the square root. Okay, so it wouldn't be a need for any parentheses. Okay, but since I'm using the 83, I have to put my argument for the square root in a set of parentheses. And now if we graph, notice that basic shape that every square root graph is going to take on. And then lastly, the absolute value. Normally there's a lot of problems graphing the absolute value because the absolute value function is not readily available. So I'm going to clear out my y sub 1 function. In order to find your absolute value, you must go within math. I'm going to scroll over to number, and ABS is the absolute value function. So notice on my calculator, it's not going to actually give me the vertical bars, it gives me a parenthesis. But I want to put in my absolute value variable, which is x. I want to make sure I close it off, right? So this is similar to a vertical bar. And if we graph, we should have a V-shaped graph. All right, so are there any questions about how to graph these things in the calculator, especially the absolute value? Because we deal with it a lot, and it's good to know how to graph that on the calculator. All right, next we'll talk about this even and odd concept. Okay, so back to the document camera. Okay, now here's the quick and dirty on even and odd functions. Okay, so this is the quick way before we take a look at the formulation and the formula and that sort of thing. Okay, even functions they have y-axis symmetry, and an even function has even powers on the variables. All right. So an even function, it has to be symmetric with respect to the y-axis. We're going to talk about that. But it has to have all even powers on the variable. So even numbers are 0, 2, 4, 6, 8. All right, so let's keep that in mind. So if I take a look at this linear function, this is x raised to the first power. The first power is an odd number. So a linear function is never even. If we look at a quadratic equation, y is equal to x to the second power. I look at my variable x, it's raised to an even power, so it would be an even function. If we were to take this parabola, and if we were to put it on an x and a y axis, and if we were to fold along the x and the y axis, the graph would fold over onto itself. All right, so when we fold it, it folds onto itself, it overlaps exactly. That's an even function. If I look at this cubic equation, I look at my power, well, I look at my variable, it's x. I look at my power, it's an odd number, so this is not an even function. All right. If I were to fold this about the y-axis, it would not overlap on itself. If I look at the square root function, it would not be an even function because if I put this thing on an x and a y-axis, it wouldn't overlap onto itself. And then lastly, for the absolute value, okay, if I look at my graph, if I were to fold this along the y-axis, notice that it would overlap onto itself, so the absolute value is an even function. Odd functions they are symmetric with respect to the origin. So notice I didn't say symmetric with respect to the x-axis. They're symmetric with respect to the origin. That means that they have both x and y-axis symmetry. Odd functions also have odd powers on the variables. So if I go back to my common graphs, y is equal to x. Here my variable is x is raised to the first power. The first power is an odd number, so the linear function is an odd function. The cubic function, it's raised to the third power. 3 is an odd number, so my cubic function is also an odd function. So now let's take a look at some further examples. just using that. It's all odd powers, it's even, or if it's all negative numbers, it's odd. So here's an example, odd or even functions. Y is equal to x to the fourth plus x squared minus 9. Okay, sorry about that. I got cut out for whatever reason. But we'll talk about is this function odd or even? So the first thing I'll do is I'll just look at all of my powers on my variable. So I have an x variable here that's to the fourth power, so that's even. I have an x variable, this is to the second power, that's even. And I also have a 9. Now the 9 doesn't have a variable and a power, but we could attach one, right? The 0 exponent rule says x to the 0 power is 1. So I'm not changing the value, but I could add in a variable and a power. Just keep in mind that all constants are even. So this would be an even function. For an odd function, y is equal to x to the 5th minus 9x to the 3rd. So if I take a look at my variables, I have an x to the 5th, which is an odd number. Okay, this 9 is a coefficient. I only want to look at my variable and my power. So I have another variable x to the 3rd power. They're both odd numbers, so this is an odd function. So we'll take a look at a last example. Y is equal to x to the 3rd minus 9x squared plus 4. So I have a variable x is to the 3rd, which is odd. I have a variable x, which is to the 2nd, which is even. If you have a mix of odd or even powers, then it's neither. Okay, this function is neither even nor odd. Okay, so I'm going to take this odd function and this even function, and we're going to run those functions through the formula. Now, this is for even functions. It says that f of negative x is equal to f of x. All right, so here's what this means. I'm going to take this previous function to the 4th plus x squared minus 9. So I'm going to write this as f of x, because in function notation, y equals to f of x. That's equal to x to the 4th plus x squared minus 9. Okay. So this thing says that f of x, which we have, x to the 4th plus x squared minus 9, if that's equal to f of negative x, then my function is even. So how do I find f of negative x? Well, in order to find f of negative x, I'm going to go back to my f of x function, and wherever I see an x, I'm going to substitute that with the negative x. Right, so I have x to the 4th, but I'm going to substitute this x with a negative x, plus x squared, but I'm going to substitute x for negative x, minus 9, because 9 carries no x. And now I'm going to simplify. So negative x to the 4th power, well, a negative times a negative times a negative times a negative is positive. So that's going to simplify to give me x to the 4th power. Negative x squared, well, a negative times a negative is a positive. So that's going to give me x squared. And then I'm going to carry along my minus 9. So notice that f of x is x to the 4 plus x squared minus 9. F of negative x is also x to the 4 plus x squared minus 9. Since both of these things are equal, this would be an even function. But the simple and short way around this is we look at the powers on your variables. Okay, but this is what this formulation means when you see it. Next, we'll talk about an odd function and its formulation. Our formulation says that f of negative x is equal to negative f of x. Right, so we're going to go back to this odd function, x to the 5th minus 9x cubed. So we have f of x is equal to x to the 5th minus 9x cubed. Now we already know that it's an odd function because all of the powers are odd. Here I'm just going to verify that by running it through this formula. So this formula says that f of negative x is equal to negative f of x. Well, I need to find f of negative x, and I also need to find negative f of x. And if these two equations are equal, then we have a function. All right, so how do we find f of negative x? Well, we'll go back to our f of x equation, and wherever we see a negative, wherever we see an x, we're going to replace that with a negative x, and then we're going to simplify. So negative x to the 5th power, well, a negative times a negative times a negative times negative times a negative is negative. This simplifies to give me negative x to the 5th I'm going to bring down or transfer over this negative and a 9. A negative times a negative times a negative is a positive. So that's going to give me a negative x to the 3rd. The negative and this negative make a positive x to the 3rd. All right, so when I simplify, I get f of negative x as equal to negative x to the 5th plus 9x to the 3rd. So now how do I find this piece, negative f of x? Well, I have to take whatever f of x is, and f of x is x to the 5th minus 9x cubed, and I have to multiply it by a negative. So now I'm going to distribute. So negative times a positive x to the 5th is negative x to the 5th. A negative times negative 9x cubed is a positive 9x cubed. Notice that f of negative x is equal to negative f of x, therefore our function is an odd function. All right, so any questions about these two formulas? They ask you for if it's an even function, then you want to put this in as your result, and if it's an odd function, okay, you may be asked to put this in as part of your final answer. Okay, and that concludes section 2.1. So next we're going to look at section 2.2, and I'm going to go to the shared screen.
I have a question.
Uh-huh.
I'm trying to do homework in section 2.1, and it's like asking the domain and range of all these weird things, and I didn't see you go over that.
Which problem is that?
Number 4?
In 2.1?
Yes.
Okay. Let me see if it may let me bring that up. Well, I'll tell you what, let me go through section 2.1 and then we'll go into that problem.
Okay.
Because I may get booted out again.
Okay.
Okay, and I'm still recording. All right, so let me open the lecture notes for 2.2, and you also want to pull out your calculator. I'm going to bring mine up once again. And we're going to talk about translations. And what a translation of a graph is, it's basically a shift in the graph. We can take a function, or in particular those 5 functions we talked about earlier, and we can shift them up, we can shift them down, we can shift to the left, we can also shift to the right. Okay, and once we make the shifts, how does the formula now look? So for the first couple of translations, we're going to talk about vertical shifts up or down. So what this formulation says, if you have y is equal to f of x plus c, your graph would be shifted up c units. And if you have y equal to f of x minus c, if you have some constant subtracted off the end of your function, then it's a shift down c units. All right, so I'm going to go back to the document camera. And so over here on the side, I have y equal to f of x. So this f of x could be any of these functions. The f of x could be linear, cubic, quadratic, square root, or an absolute value. Right? So you have y is equal to some function. If you were to add a number to the end of your function, it would shift up c units. So if you have y is equal to f of x plus c, it's a shift c units up. If you have y is equal to f of x minus c, it's a shift down c units. All right, so here's what that means. Let's say we have y equal to x squared. And we're doing like some basic hand-drawn graphs. Right. If I wanted to take this basic graph, and let's say I wanted to shift up 2 units. So here's what that means. So here's 1, here's 2. If I want to take this basic graph and shift it up 2 units, what does my formula look like? Well, based on what we have over here, if I wanted to shift this graph up 2 units, I would simply add 2 to my function. So y is equal to x squared plus 2 would shift that graph up 2 units. If we wanted to shift down 2 units, I can get it right over here. Okay, if we want to shift down 2 units, 1, 2. So I'm taking that same graph and I'm shifting it down 2 units. Right? So I'm taking this graph and I'm just moving it down 2 units. Right? Well, what does my formula look like? Y should equal to x squared minus 2. Right? So this is a shift up 2 units. Okay, a shift of the basic function. And then this is a shift down 2 units. Okay. So I'm going to just take a look at this in the calculator. All right, so I'm going to take that same x squared graph. So I want to go into y equals, and I want to put in x squared. I'm going to hit zoom 6 to graph, and we have our parabola. I want to go back into y equals. I want to go to y sub 2, and I want to put in x squared plus 2. What should happen is it should shift our basic parabola up 2 units. All right, so notice that's a vertical shift up 2 units. I want to go back into y equals, and this time for y sub 2, I want to put in x squared minus 2. And if we regraph, notice that there is a shift down 2 units. All right, so if you add a constant to the end, that shifts up. If you subtract the constant from the end, that's a shift down. All right, now let's look at horizontal shifts, and these are the left and right shifts. And this is where things get a little bit sticky, because what physically happens doesn't match what we actually write out. And here's what I mean by that. When you shift to the right, or when you move in a direction to the right, if you're following an x and a y axis, to the right would be a positive movement. But actually, in these formulations, when we shift right, we actually subtract the number off. Mathematically, when you move to the left, right, that's actually a negative direction. However, when you write out your function, we write with the plus. So here's what I mean by that. So notice it says that if you have y equal to f of x, y equal to f times the quantity x minus c is a shift to the right. Y equal to f times the quantity x plus c, right? Normally plus means right, but actually notice a shift left. Okay, so let's look at these two in further detail. All right, so going back over here to our formulations, if we have y equal to f times the quantity x plus c, That's a shift left. So that's C units left. If you have y equal to f of x minus c, that's a shift c units right. All right, so let's re-examine these. If we wanted to take this x squared graph, and let's say we wanted to shift to the right 2 units. All right, so physically, this is what I mean. We're taking this graph, we're shifting to the right 2 units. What should my function now look like? So we should have y is equal to, now notice since I'm shifting to the right, the formulation says it's f of x minus c. So I want to write this out as x minus 2 quantity square. So notice that this minus 2 is within my function. This minus 2 is attached outside of my square term. And we're going to grab this in the calculator in just 1 second. All right, now conversely, let's say we want to take this graph and shift it to the left 2 units. So to just draw out what that looks like physically. All right, that's 1 unit, 2 units to the left. And we want to shift the graph 2 units to the left. All right, what would our equation look like? Well, from our formulation, it says y is equal to f of x plus c is a shift left c units. So I want to write this out as y is equal to the quantity x plus 2 squared. Right, and that should shift left 2 units. So let's take a look at these on the calculator. All right, so I'm going to go back into y equals. I'm going to clear out y sub 2, and we're going to put that right shift function. So I want to put in a set of parentheses, x minus 2, close off my parenthesis and square it, and this should shift our parabola to the right 2 units. Right, so now we just shifted that parabola to the right 2 units. Even though you're shifting to the right, we're subtracting within our function. So that's a shift to the right 2 units. If we wanted to shift the parabola to the left 2 units, I'm going to go back to y equals, and for y sub 2, I'm going to change the subtraction to a plus. And if we regraph, notice that it's a shift left 2 units. Now, in the next few sections, we're going to talk about how to reflect across the x-axis, how to take a function reflected across the y-axis. We're also going to talk about vertical and horizontal shrinking and stretching. Okay. So in our next section, we will build upon our model forms. Okay. And what I mean by model forms are, I'm going to return to the document camera. Okay. And by model forms, I mean these. Right, we can modify our equation to reflect across the X or Y. We can modify our equation to horizontally shrink or stretch a function. All right, so any other questions about, we'll go back to that section 2.1 questions, but any questions about section 2.2? All right, so at this point, I'm going to stop the recording.